We're ready to analyze the tipping portion of our lab. We'll start by defining the center of mass of the object as the average location of all the mass in the object, and we'll assume that the center of gravity is in the same location as the center of mass. That approximation is good for small objects that we will be analyzing today near the surface of the Earth. The force of gravity acting at the center of mass, in this case, will cause a torque. That torque will either cause the object to rotate into the hill or away from the hill. If the center of mass is located or uphill of the lower edge of the base of support, then the object will tend to rotate into the hill, in which case the normal force acting on the bottom of the object can provide a counter torque around that rotation point to cancel out that torque caused by gravity, and the object can remain in static equilibrium. On the other hand, as the slope becomes steeper, eventually the center of mass will be moved to a point beyond the edge of the base of support here, which acts as the rotation point, and that torque caused by the force of gravity will cause the object to rotate away from the hill, in which case there is no force available to cause a counter torque to cancel out the torque caused by gravity. The normal force can only push up from the surface, so that is not an option for causing a counter torque. I would need a force that pulls down on this side of the object. It would have to be anchored. But in today's lab, we're analyzing objects that are not anchored, and so there is no force available to cause the counter torque to gravity, and the object will rotate. If I am at exactly the right angle, so that I have reached the point where the force of gravity passes through the rotation point at the edge of the base of support, then this is the maximum angle, maximum slope that I can achieve before tipping. Any farther and the center of mass will move beyond the edge of the base of support. So this is my maximum angle before tipping. In that case, I can draw a triangle, and what I see is that the height of the center of mass above the bottom of the object, which we will call h, that's the height above the bottom of the object if the object were flat, we'll call that h. So that's this distance. That distance and the horizontal distance from the center of mass to the edge of the object, which in this picture here, that distance is there. If the object was flat, it's a horizontal distance. When the object is tipping, it's here and it's parallel to the surface. That distance we'll call d is from the center of mass to the edge of the object. I can see that the angle here in this triangle I've drawn is the same as this angle in my large slope. Therefore, I can relate these two triangles. In fact, the slope of my large triangle, which is the rise over the run, rise over the run, or alternatively is equal to the tangent of the slope angle. I can relate that to the height of the center of mass and the distance from the edge of the object. Using this similar triangle, I can say tangent theta is equal to distance of the center of mass from the lower edge of the object divided by the height of the center of mass from the base of the object. In that case, I can then define the slope as the distance of that height, or the tangent of the slope angle as the distance over the height.